Hello, everyone. So Benny is, I think he's in a conference, so he cannot chair for today's talk. I will substitute him to chair this today's talk. Today's speaker is Jie Han from Beijing Institute of Technology. He will talk about rainbow threshold. So please.
Okay, thank you. Thanks for the invitation and also the introduction. Today it's my great pleasure to talk about some of the recent work on random graphs. This is a joint work with Xiaofan Yuan, Dr. Xiaofan Yuan. She's a postdoc in Arizona State University in the US. And actually when she was an undergraduate student in USTC, and she was a student of Professor Jie Han. Okay, so what do? We consider random graphs, and then for graphs we mean undirected and just simple graph on a finite set of vertices. And then the random graph model we consider will be the traditional GNP model, where you have a set of n vertices, and every two of them you connect by an edge with probability p. And all these choices, you have n choose two choices. All of these choices are independent. And then what we will talk about extends naturally to random hypergraph, but probably we don't go that further. The hypergraph in this talk will be for this spread or abstract setting. So when I talk about hypergraph, I will just mean a family of subsets of finite set X. Okay, I'll try to make it clear. So what do we study for this random graph problem? There's a typical and actually classical object called thresholds. So this is what we like to study when we look at graph properties. And the graph properties just means a collection of graphs. And then we will deal with increasing ones because this will be easier to understand. And people discovered actually Erdős and Renyi in the paper that they introduced the binomial random graph. They discovered that a surprising property called threshold for graph property. So they found that given a property you want, so there could be a function p0. It's not a constant; it's a function of n. And then when p is much bigger than p0, and which just means p divided by p0 goes to infinity. And then GNP with high probability has this property. And with high probability means the probability that the property holds goes to 1. The probability goes to 1 while n goes to infinity. And for the other case, when p is much less than p0, and which just means p divided by p0 goes to 0. And then GNP with high probability does not have this property. So this is really an interesting phenomenon. And then they found that actually it is this threshold behavior it really holds for many properties until in '87, Bolobach and Thomason proved that every increasing property has a threshold. So this is nice result. However, it doesn't really give you information about the threshold, like how big it is. So here are two simple examples when we talk about Hamiltonicity, namely when does your graph have a Hamiltonian cycle, a cycle passed through all vertices exactly once. And then the threshold is log n over n. Another example is for connectivity. So when does your graph, when does your random graph, or when is your random graph connected? The threshold for connectivity is also log n over n. And then they two actually, this log n over n has actually has an interpretation. It is where when your last isolated vertex, when your last vertex it has degree 1, and that's clearly necessary for connectivity.
I just have a question. So when you say increase in property, you mean if a graph is satisfied with property, then his super graph also satisfies the property?
Yes, exactly. Yes, exactly. Right. Right.
Okay.
Yeah, thanks for the question. Right. So if a graph satisfies this property, when you add more edges, or let's say one edge, you doesn't destroy the property. And then when I say increasing, it doesn't really make a difference because you can always, you can deal with the decreasing property in a similar way because you can always consider the complement of the graph. So it's kind of a monotone property. Graph property, but I was not bothered with that, so I just put increasing. Okay, right. So yeah, okay. So log n over n is actually the threshold when your last vertex from isolated vertex have degree 1 or 2. So that's when actually that's a clearly necessary condition for connectivity and Hamiltonicity. Okay, so again, as I try to say, this Bolobash-Thomason theorem doesn't give you the threshold; they just tell you it exists, and then determining the threshold for various properties became a central problem in random graph theory. So there has been many excellent results and works until they are kind of individual. Some of them are broader than others. Until Kahn and Klein made the following conjecture, like inspiring conjecture on the thresholds. So what they do is the following. So one thing called expectation threshold is the following. So we can always find a lower bound for the thresholds as follows. To be simple, let's think about the property is containing a subgraph F, or containing F as a subgraph, sorry. So to be simple, let's consider this is my graph property. Okay, I want my GMP to contain F as a subgraph. A necessary condition is that the expected number of copies of F in GMP goes to infinity. So if this expectation doesn't go to infinity, you can use a simple Markov inequality showing that actually, you have a small chance, but a fixed chance of say epsilon that this probably doesn't hold. So then you lose the game. So this is a natural necessary condition. And then Kahn and Klein made an inspiring or even bold conjecture saying that actually this almost gives you an upper bound. So their conjecture reads as follows. So if P prime is the smallest probability P so that GMP satisfies above, P prime log n, because F has at most intrudes two edges. Right. So this log n is necessary in general because of known results. Actually, from the two results from above, both Hamiltonicity and connectivity, if you compute the expectation threshold, they are just 1 over n. And you do 1 over n, they are not thresholds. You need log n for to cover all the vertices, for that simple reason. And then they conjecture that this is just it, right? So what they mean is I want my threshold for my property, or just for F. And what they conjecture reads as follows. So this is lower bounded by P prime and upper bounded by P prime log n. So this with a narrow window. Sometimes it doesn't exist, and sometimes it exists. Okay. So that is the conjecture. And it's still, and this conjecture is still open. But the major breakthrough in the recent years are actually the fractional version and the abstract version, and then the fractional version of the abstract version have been resolved in recent years. So to talk about this abstract version, let's quickly introduce this abstract setting. So we are going to talk about this abstract setting. And to do it, actually, one more sentence I should say is, why do we need abstract setting? The problem is actually because this excitation threshold itself is not so easy to compute. So I said contain f as a subgraph. This looks simple enough, but even for this, we don't have a we don't have a simple calculation or universal calculation tells what is p prime is, because f may not be balanced. Namely, f might be some large graph, but actually the threshold of f is achieved by a small subgraph. Say you have a Hamiltonian cycle, and then you put a clique somewhere. You have a clique of 1,000 vertices somewhere. So this makes it complicated, and actually we can't really simply compute the excitation threshold. And then they put up abstract setting. Actually, this was put by Kahn and Kalai for this abstract setting. So they made two conjectures, one for the graph setting, one for this abstract setting. So as follows, okay? So I fix x. So x is a finite set. And then we consider a hypergraph, namely a collection of subsets. So H might be just a subset of 2 to the x. I don't need it to be uniform. And then given a set S, a set S, let the span of S to be the upset, right? For each S, you take all the sets containing S, and this is the span. And then given the hypergraph H, I can also define the span of H, which will be, I take each set, make up upset, take each set, take upset, and then take a union. So this will be the upset. And then this H, this hypergraph H, is called the chi-spread. This will be the main definition. If it's chi-spread, if given any S subset of vertices, or I mean elements, I don't have vertex edge here, given any subset of elements S, then H intersect the span of S is at most H over chi to the S power. So how this looks abstract, how do you understand this? So I want, so the name is called spread. So what do I want? I want the edges of H, or the sets of H, spread evenly in my universe in X, right? In capital X. I want it spread in the as even as possible. I mean, I don't need as even as possible. I want it to be even. Okay. What I don't want like say 1 point, or I don't know, 100 points. They occupy all the edges, and that is not spread. That is bad. So that means for my S, for any S actually, if I fix X, I don't see many edges contain this X, right? So how many? At most this. At most H divided by chi to the power of S. So this factor or fraction must be related to S itself, right? So that's how we make it. That's it's chi to the power of S. So it will decrease very fast regarding to the size of S. So right, this is the key definition. Maybe I don't elaborate enough, but later we will see an example for Hamiltonian cycles. But anyway, this is a definition of a chi-spread. I hope you buy it. And then this is the conjecture made by Talleyrand, and this is what I mentioned for this fractional version of the Kahn-Kalai conjecture, fractional version of the abstract version of the Kahn-Kalai conjecture. And Talleyrand made it in 2010, and now it's approved by Frankston, Kahn, Narayanan, and Park in 2021. I mean, they post on 19 and published on 2021. And it reads as follows. So there is a universal constant K, and then such that for every L uniform chi-spread hypergraph H on X, uniformly random element subset of S belongs to span of H with hyperability. So what does it say? I give you a set X, and I fix a hypergraph, and the hypergraph will be the object you, the collection of the object you want. So I'm hunting for some structures, and the collection of them are the hypergraph H. I'm happy if I catch one of them, any one of them, I'm happy. And then what does the theorem say? The theorem or the conjecture says, if you pick uniformly random amount of them, how many? The quantity I marked. So what does it mean? This means you take a fraction of the vertices. And what is a fraction? Essentially, it's log L over chi. And because bk is arbitrary, bk is a universal constant, and size of X is the size of the universe, right? If you pick it with this probability log L over chi, then you win. Okay, this is what he said. Then you win, which means you capture, with hyperability, you capture one edge of H. Okay. So that is the theorem again. And then here is the example. Here's an example. Okay. Or how do we, so why does it work? Like, how do we use it? Actually, we can use it as follows. So let's look at Hamiltonicity. To understand Hamiltonicity, we do the following. Let capital X to be all the edges of a complete graph on vertices. That's formally I made it like bracket n choose 2, which means all the pairs A, B, C, D, A, C, B, D. And then let H be the collection of all Hamiltonian cycles on bracket n. So how many Hamiltonian cycles? Is kind of you list the vertices in an arbitrary way, and then you get n factorial of them, but not exactly, because when you make them cycles, it doesn't matter where you start. So it's n factorial divided by n. And also for each cycle, you have two ways to go, and then you should divide by the other two as the multiplicity. So anyway, this number or the number of sets in this hypergraph will be n minus 1 factorial over 2. And then actually it's straightforward to verify that this hypergraph H is n spread. I won't do it, but it's straightforward. And then the theorem we have seen, the theorem above there implies that the threshold for Hamiltonicity is log n over n. The n here is just the chi spread, the chi here, but the chi now I know it is n, so log n over n. Then we immediately done, and then recovers this old result on Hamiltonicity. And then to say like it is like chi spread or whatever spread, and then we need to fix a bunch of edges, right? And then say how many, for example, this is my capital S. And then how many Hamiltonian cycles contain these edges, right? That it will be the spread assumption that you need to verify. Okay, and this is the reference for the paper. The following natural setting has been considered by Alan Frieze. Yeah, he likes more, so he wanted more. We are doing somehow. One more comment. Sorry, one more comment from the conjecture or theorem. One more sentence is that for the theorem or conjecture itself, they didn't state it as L uniform. They only say L bounded. Namely, H doesn't need to be a uniform hypergraph, but we just need to put a bound on the maximum size of the edge. But to simplify my presentation, I put it L uniform, even here and also for my own, our own results. But just to simplify the presentation, also we have a small proof at the back. So this will be easier. So the this L uniform is actually not needed. Okay, so let's come back to the setting of rainbow setting by Alan Frieze. It reads as follows. So again, let's H be a hypergraph. Let me do L uniform hypergraph. And what is the smallest P? So that if we randomly color X with L colors, and then we choose a random set of P times X vertices, and then it contains a rainbow edge of H. Okay, and the rainbow here means all vertices have distinct colors. Okay, so if we ignore about the color thing, and then this is exactly the setting considered by the previous theorem. Okay, so Alan Frieze wanted more. He wanted to be when you catch, right? When you capture your edge, you actually capture a rainbow one. Say your edge have 5 vertices, and all five elements, all 5 of them receive different colors, completely distinct colors. So that's what they want. Okay, and these actually have applications to the model randomly colored random graphs. So this is again like a general setting and potentially for every problem. So given like a subgraph F, like a graph F, so when does GMP contain F? This is increasing property, and then it has a threshold function. And now, if I have my GMP, I randomly color the edges with a fixed number of colors. And when do I have a rainbow copy of F? So there's a similar threshold function, and then you may call it the rainbow threshold, or we should call it, or we may call it rainbow threshold. So the rainbow version. Okay, and then it's you have a random graph, and then you randomly color the edges. Okay, this is the setting, and then our results essentially reads very similar to the theorem I presented before, except that you now randomly color. Okay, so let A to be an L uniform chi-spread hypergraph, and let X be to be the vertex set, and I randomly color it by L colors. Actually, I can easily say L colors, but if we just say if I do more numbers, it's fine because they are only helping us, right? Q is at least L colors, and then there is a universal constant K such that uniformly random this many elements subset of X contains a rainbow edge of H with high probability. Again, this is almost identical except that I randomly color the vertex set of X. Okay, and this resolves a question of Bell, Frieze, and Marbach, who actually showed the same result above, with the additional assumption that the subbrightness should be linear in N, should be at least linear in N. Okay.
What is N here?
N is sorry. I think N is I think is if we plug into the original notation, I think about the N is the number of vertices of the random graph. Sorry, so that must be correct, and then that means we don't necessarily have it here.
I see.
Yeah, so I don't have it in my notation, sorry. Yeah, I should spell out the random graph version then, right? And and luckily we remove it. Thanks for the question. Okay, so what do we do? How do we prove it? Okay, we prove it by proving a transversal version. This transversal version, I'm going to introduce in a few seconds. And actually, Frieze team, they also actually observed this, but somehow maybe they don't know what to do with it. But yeah, let me state it as follows. So it looks more complicated, but it's very similar. What does this do? So you have a L uniform chi-spread hypergraph, and then you look at the vertex set. You create the colored vertices. This. So for each vertex, say I have L colors, I create this duplicate, like X with my color 1, and X with my color 2, and X, sorry, this is comma, X with color I. So I duplicate the vertices. And now my hypergraph or my target hypergraph will be the following. So the vertex set will be X prime. Namely, I now have the size of X times L, this many vertices. And now I put the edges to be just the rainbow edges. Namely, I put this X1, C1 until XL, CL as a hyperedge in my H prime, if and only if the X coordinate for my edge of H and the C coordinates are completely different. So this is just a simple rainbow edge, and it's quite similar to this rainbow setting. So what is the difference? The difference is, say, for all these vertices here, only one of them, actually at the most one of them can appear in my rainbow version. Oops, in the rainbow version, right? Because you, after you pick the edge, you randomly color it. So you have at most one such edge. But in this transversal version, we allow multiple of them, not at most one. And then we say, oh, this is the model, and you want to do some random selection. Your goal is to hit a rainbow edge. Okay, so here is the threshold. There is a K, capital K, like universal constant. Then if you uniformly randomly choose a set of this many elements, then you hit a rainbow edge. Namely, you hit an edge of H prime with high probability. Okay, so they are kind of a parallel but very close settings, because there's only difference is the like how many colors can you see actually. Okay.
So here is X, the size of X or the size of X prime?
Say it again.
The
size of X, the size of X. So later you will see from the computation actually, because later I show it is L chi spread. Then the L and this L will cancel. So somehow you see the next slide or so. Yeah, this is correct. This is correct. Yeah. Okay. Right. I will prove the rainbow version by proving this transversal version and then connect them. And then both of them are easy actually. Okay, so so this first I want to show the transversal version, but I reduce it to the uncolored version. Okay, namely to the result of F, K, and P. Okay, so this is actually observed by this Bell, Frieze, and Marbach, and as follows. So if H is chi-spread, and then H prime is L chi over E spread. Okay, so what is H and H prime? H is the target hypergraph, and H prime is obtained from H. These are only the vertices, right? I add the colors in, right? I add all rainbow L vertex colorings, right? In the arbitrary way. So clearly, the size of H prime, right, equals the size of H times L factorial. Okay, so what I say now, I give up on Q. I just say let's fix L colors. Okay, times L factorial, and then what do you do? I want to show it is spread, and I will just hit the definition. Okay, to hit the definition, I take or I fix a set of vertices. This is set capital S of vertices of VH prime. So what are they? They are this set. They have x1, c1, x2, c2, They are not just vertices, they are colored vertices, right? Maybe xi, cs, but we're not needing it. So first, if this S is not rainbow, right? If in capital S, you have two vertices sharing the same color, like Ci equals ECJ, right? Then you give up. Because if S itself is not rainbow, it cannot be in any rainbow edge. Okay, we give up immediately. Or this quantity is zero. The quantity we're hunting for is zero. So it remains to say, okay, now suppose S is this rainbow. So the C1, C2 until CS, they're all different. And now we compute how many copies of how many rainbow edges containing it, or like how many edges of H contains it. Okay, so and then we start looking at this is we want to show H prime is spread. So this is the notion we want to show, and this is of course the goal, right? And now it's filled up in the middle. So first, if we fix like we have capital S, if we fix the x coordinates, so they are x1, x2, x3 until xs, right? If we fix the s coordinates, the just uncolored version, right? So by the spreadness of H, right? By the spreadness of H, I know it is in this many edges of H. It's like say simply temporarily say, let's forget about the colors. I can extend this x coordinates of S into this many edges of H, say without colors. Okay, and what about the colors? S itself uses this many colors, and for the rest of the colors, I choose arbitrarily. Okay, and that's the number of choices is exactly L minus size of S factorial, because this many colors has already been used here, and for the rest, I must use all of them. Not arbitrarily, I need to make a rainbow, but kind of arbitrarily because I can use any pattern I want. So it's L minus S size of S factorial. And then I can do some calculation. In particular, now I use this equality. Now I use this equality, rewrite that. Oh, now I know the size of H equals size of H prime divided by L factorial, and then put L factorial in the bottom, and now this L minus S factorial divided by L factorial becomes this descending factorial down in my denominator right here. And then for the last step, I just use a basic inequality involving this estimates on the lower bound on S factorial. And we're done. And as I said, this is a simple proof. And as I said, actually Frieze, they also observe it. Although their model is slightly different. I mean, they define something slightly different, but somehow doing the same thing. We say, okay, well, yeah, right, and the same proof, same and a simple proof. Okay, so we just show that if H is spread, then H prime is spread. Okay, and then what do we do? And then because this H prime, this rainbow or colored version is good, then we just apply the theorem of FKMP. So this, and then we're done. The reason is the number of vertices is x times L by this FKMP. If we select a set of random uniformly random elements with this many elements, then we win. Okay, this is what FKMP tells us. Why? This is a universal constant given by their theorem. and this is the size of the universe we have, and this is a log thing depending on the L uniform, and then this is the spread. So we literally plug in their results and get this. And now to get our result, and also actually the quantity Jie was asking, we cancel the L then. Sorry, we cancel L and we put E upstairs. So, right. Yeah, and that's the proof for this transversal version, but actually it's kind of a corollary of the uncolored version. Okay, everything fine? Okay. Yeah, and then I mean, then we are done for here, right? And then we prove the transversal version. We want to say actually also implies the rainbow version, and then we are done, right? So for that, we use a coupling idea of macadamide. A very nice coupling idea. So what do we do? I will raise something, but again, let's think about random graphs. We'll make it easier. So for for the short proof, I will only think about random graph. For that, I fix Kn. I mean the edge set of a Kn. There are choose two edges. I mean, let me give it an ordering arbitrarily. Arbitrary ordering E1, E2 until En choose 2. This will be the edges. And then I consider a sequence of processes. Okay, so T0 up to Tn choose 2 as follows. Okay, what are my processes? Ti, okay, is the model where I'm doing my thing, but model is for the random graph model, where the first I edges are drawn by the rainbow model. Okay, so this is my Ti, and then I'm considering this N choose 2 edges, right? So the first I edges are drawn from the rainbow model, and the rest of N choose 2 minus I, and the rest N choose 2 minus I edges are drawn by transversal model. And I have a common, and then, okay, yeah, I think this is important, but I think this is simple.
Sorry, can I ask a question?
Sure.
I thought the rainbow model means you randomly sample some fixed amount of edges and then you color them. Is it correct?
Right, sorry. Now you're right. Now I switch from the GNM model to GNP model, and they are somehow equivalent when you study Moses properties. And what I mean is, for both questions, actually for both transversal and rainbow models I mentioned in the slides, is I choose a fixed amount of edges. And now I don't do this. I choose each edge individually in the binomial sense. For each edge, I flip a coin. And this is the GNP model.
This means that in rainbow model, you pick an edge with probability P and then color it. And for transversal model, for each colored copy of each edge, you sample with some fixed probability.
Exactly, that's perfect. Yes, exactly. Right. So for rainbow model, I do like two decisions. I choose or don't choose this edge, and then I randomly give it a color. And for transversal model, I have all these copies, and I flip a coin one by one. Do I have the X with first color, second color, third color? I do one by one. Yes, thanks. So this is my model. Actually, I have a list of these models. They are all different, but they are close. Okay, if I do this, T0 is the transversal model, because right, T0 means the first 0 edges are drawn by the rainbow model, right? So T0 is just a transversal model, and Tn choose 2, my last process, is exactly the rainbow model. Okay, and let me define the event I want. The event will be EI will be the event that Ti contains F as a rainbow subgraph. Okay, this is my common goal for all the processes, and the claim is the probability for the En choose 2, the last one, is at least something until at least the PE0. So right, so this is the probability of my rainbow, sorry. The first one is my transversal model, win. And the first is probability of my rainbow model wins. And if I prove this claim, then we're done. Okay, this is at least that. Okay, and now I think I have time to elaborate on what is going on here. And I'm going to prove it for one by one. Now doing the induction, I can analyze Ti and Ti plus 1. Okay, so for Ti and Ti plus 1, and the first the first I edges are drawn by the rainbow model, should be as this. And this, where this behavior changes, is my I plus 1. Yeah, everything looks good. Those are my edges. The first I of them in my Ti are chosen by the rainbow model. And for next line, Ti plus 1, the first I plus 1 of them are edges of them are chosen by the rainbow model. Okay, so I look at these two models together. Their only difference is EI plus 1. How I choose EI plus 1, by the rainbow model or by the transversal model. Okay, when I compare these two, I have 3 cases. Okay, I have case 1. Case 1 is I win without considering EI plus 1. Okay, this means I look at other edges, I already win. Namely, I got a rainbow edge. And this is the always happy case. And case 2 is I lose even. Sorry, maybe one sentence before this. I'm doing the following. I first expose all other edges except EI plus 1. Right. Let me write first. Expose all edges except EI plus 1. And then for these two models, they are equivalent now. They're equivalent, right? And I have 3 cases. The first case, even without looking at EI plus 1, I already win. Okay. The second case is I didn't win, and I don't win, and even I have all colors. Definitely I don't have all colors in my transversal model. Even I can get any color on EI plus 1. Okay, the second case is I lose even if I get any color on EI plus 1. I lose. And this is the always unhappy case. So, which means I already checked all other edges, and I need something, and this EI plus 1 is not enough. I already lose, right? It doesn't matter. So again, actually, the first case I win with probability 1, and the second case I win with probability 0. Okay, I don't get my rainbow copy, and what is left? The case 3, what is left is this is a non-trivial case, right? This like case 1, case 2 doesn't happen, they don't happen. So I have a non-trivial case, which is the following. So there exists a set L. Let me maybe don't call it L. Let me call it C as a set of colors. Is a subset of my colors such that if I get a color, or if I, let me just say, if I get EI plus 1 with color C in C, then I win. So this is crucial, because I don't always win and I don't always lose. So then it's non-trivial. So there exists a set of colors, maybe only one, maybe L minus 1, a small L minus 1 of them, that if I get those colors or one of those colors, I win. But this is the non-trivial case, right? The first case means it doesn't matter which color you give. Actually, even if you doesn't give me EI plus 1, I win, right? The second case, you give me any color, I lose. So this is a non-trivial case. And then if I consider, if I compare the success probability for these two models, only case 3 matters. Because for case 1, if I expand this by conditional probability, phase 1, I win out anyway with probability 1. I said it, but let me repeat it again. And for the second case, I lose with probability 1. So I win with probability 0. So only case matters is the case 3. Okay. And let's compute. Then let's compute the success probability within this. So for case 3, what is the probability of win even case 3? So I have two models. So first, let's look at the PI, which means EI plus 1 is chosen by the transversal model. Okay, choose by the transversal model. Then what do I win? I have a couple of colors, like capital C. If I get one color from there, I win. So I may lose. My probability of win is 1 minus PR. I didn't say this. I didn't say the probability for this model. Sorry. For the rainbow model, I pick an edge with probability P, and then I color it with like 1 out of L colors, right? For the transversal model, I pick any colored edge with probability P over L, right? So if I combine them together, I get probability P. So these are the two models. Okay, so for the transversal model, I lose if for all these possible colors, like out of the winning colors, I fail. So this is for the winning probability for the transversal model. And for the rainbow model, I win. First, I need to pick an edge. We need to win on the edge EI plus 1, and then the second stage when we make the color, choose the color, I need to win. I need to choose the color out of C, so C over L. So this is the winning probability for the rainbow model. And I think I don't do the further calculation, but this probability is just larger than the other. Okay, and that's the end of my talk. If there's no question, but yeah. Okay.
Well, thank you, Jie. Very nice talk. So if you have any question, just free yourself and you can just go ahead.
I have one question. My understanding is that in this uncolored setting, there have been this fractional version, and later there has been non-fractional version.
Right.
In work. Is there some analog of the non-fractional version in the rainbow setting for Kahn-Kalai? And is that something that you work on, or?
Yes, thank you for the question. That's yeah, I kind of skipped it in my talk. Such a version exists. I mean, such a version is possible, and you can try to prove it. We tried hard to prove it, and somehow this fractional version is easier, and that one we didn't make it to. We didn't prove it as what it is. But luckily, due to this. Actually, due to the resolution of this Kahn-Kalai conjecture, this conjecture, now is a Park-Pham theorem. Actually, this conjecture, we can use this. Because I didn't give the definition, right? So actually, we can prove for the actual version, the non-fractional version, we can prove that with this probability, and will be wrong by at most 1 log n, because they two are kind of connected together. And then, well, if you have a direct proof without the second log, that'll be great. But also, this will follow from another conjecture of Telegram, who conjecture that this expectation threshold is not the expectation threshold. This this p small and fractionally p small. So this p small is bounded by weakly p small. Again, sorry, I'm not introducing those definitions, but somehow I was just saying we tried it, we failed. Using this Park-Pham theorem, we can get somehow we lose by a factor of log, and if another conjecture of Telegram holds, then we win immediately. So okay, thank you for the question.
Thank you for the answer.
So I have a question. So you consider rainbow coloring. What if I, fix some coloring which is not rainbow? Say every edge is every color is exactly appear twice. Then what happens?
Then every color appear at most twice. Well, I don't have a quick answer. So what I can say is we have this simple proof for the rainbow version, because the coloring is like, we're going to consider rainbow colorings, and they are really symmetric. You can move it in the arbitrary way. And then, so when you have further color patterns, if they also have like high symmetry, then of course it works. But if not, then I don't know what we'll do. Maybe we need to do some real work instead of getting the corollaries. Yeah, like there's a corollary. Yeah.
I see. Very nice talk. I like your result. Do we have other questions?
Yeah, so maybe just a comment related to this 2-color version. I think if for every color, make 2 versions of the same color, kind of fake versions, two copies of the same color, find a rainbow version there, and then that will actually have, you can kind of reduce it just as a black box. You will have every real color appearing twice because it appears in 2 fake variants.
Okay. Thank you. Okay, so I think let's thank you again, Jie, for the wonderful talk, and we can stop the recording.